Welcome at the second part of the morning session. So there are a lot of changes. Our speaker is Wolfgang Wieland, and also the title has been changed since the first version. So if you didn't refresh your this view of the website, then you may be surprised. So the title is Quantum Geometry of the Light Cone. Wolfgang, the floor is yours.
Hello? Yeah, you can hear me. So before starting out my presentation, let me first thank the organizers, Mushin Han and Jonathan Engel, for inviting me to Florida to this very nice conference. I would also, what I want to speak about is actually the result of somewhat a long journey, and Abai was very kind to mention very briefly some of the earlier results. And today I want to tell you about the latest results and then important updates. And I would also like to take this opportunity to thank my colleagues from Erlangen, so Christina Giesel, Hanno Salman, and Thomas Thiemann, that gave me the freedom to pursue this research. Let me start out with a simple observation. Simple observation in classical general relativity. So if we consider d = 4 space-time dimensions, something funny happens, namely that the Planck luminosity, so if we take the Planck energy and divide it by the Planck time, the resulting expression turns out to be independent of h bar. So h bar cancels out from this expression for the Planck power. So this is the Planck energy divided by Planck time. And this is something that indeed only can happen in d = 4 space-time dimensions. And this has important physical consequences, in fact. So if we take, since the Planck power is independent of h bar, it means that it can actually appear at the classical level, at classical equations. If we look, in fact, at the coalescence of two black holes, then and the gravitational wave profile, there will be some oscillatory phase. Then the luminosity will increase until the ring down when it goes down again. But since the Planck power is independent of h bar, this L Planck, Planck luminosity can appear at the classical level, setting a scale for the peak luminosity. And whatever else appears in this equation must be scale-independent quantities, like the mass ratio or independent dimensionless spin coefficients. And this suggests, in fact, that so the Planck power can already appear at the classical level. And in fact, we have more than that. There's a simple argument that you can find in Misner-Thorne-Wheeler that the Planck power could actually be a threshold. So if we look at a self-gravitating system that emits gravitational waves, we can estimate the luminosity using the quadrupole formula. What enters the quadrupole formula is the frequency at which things oscillate, the mass of the system, and its scale, so its size. But then we also know that if the system is self-gravitating and we apply Newton's law, there will be a relation between the frequency, the mass, and the size of the system. But now if we also take into account that emission can only happen as long as we are larger, as long as the system is larger than its gravitational radius, larger than the Schwarzschild radius, then we, back of the envelope calculation gives us a bound. And in fact, if we look at gravitational wave events, we came somewhat close. I mean, 3 orders of magnitude close to that bound. And I think this is an opportunity for us, for a new phenomenology where quantum gravity effects could leak into the classical theory. And in fact, we know that something similar happens in 2+1 dimensions, where the role of the, instead of the Planck power, the role that the Planck power could play for quantum gravity in 4 dimensions is played by the Planck mass. Because just like in 4 dimensions, the Planck power is independent of h bar. In 2+1, it is the Planck mass that is independent of h bar. And in fact, already in classical GR in 2+1, if we couple point particles, we also get a bound, namely that the ADM mass is bounded from above by this value, simply because it is a deficit angle. And this has been explored in relative locality, but also in loop quantum gravity, for instance, by Corici and Ashika. But now, what I want to argue in this talk is that quantum gravity could actually play a role in this story in 4 dimensions. And this is based on new results that I will present in this presentation. A few points of caution. So first of all, what I said in the previous slide, the bound can only appear in 4 space-time dimensions for dimensional reasons. Furthermore, G Newton appears in the denominator, so it is impossible to see at a perturbative level. Yet, there is an important point of caution. From the perspective of the physics at null infinity, there's indeed no good reason for such a bound to appear. Because at null infinity, the asymptotic shear is the free radiative data, and there is no reason a priori why the shear should be bounded from above. But how could we possibly explore this scenario? And the basic idea is to register gravitational radiation at the null boundary. At the null boundary, at the light-like boundary, we have more structure available. And so in loop quantum gravity, we usually think of space-like hypersurfaces and then characterizing Dirac observables on these space-like hypersurfaces by introducing, for instance, deparameterization, the program that Bianca also studied in loop quantum gravity. But I think there is perhaps a shortcut doing the same in a different way. Now take the ADM initial data and then we have to impose constraints, namely the vector constraint and the scalar constraint. And this constraint generates gauge redundancies. So if we solve the constraints on one hypersurface and then take the Hamiltonian flow of the constraints, they generate new initial data on a slightly deformed initial hypersurface. I'm looking here at partial Cauchy hypersurfaces that have corners. But the point is that the initial data on these different slightly deformed hypersurfaces are actually gauge equivalent. So these different hypersurfaces carry the same gauge equivalent state. And now the idea is to push this gauge evolution to its natural extreme, namely the boundary of the future Cauchy development of the initial domain. And this is in fact very much similar to what we heard on Monday, I believe, where also we were solving the constraints by pushing towards pushing the gauge evolution to its extreme. So Raju was talking about evolution in ADM, in DS, de Sitter, pushing to asymptotic infinity. Here, I'm pushing towards a null boundary. And then the idea is to pick the data at the null cone, at the null boundary, as the unique representative of the physical states in the bulk. And this will then allow us to register the radiative modes at the null boundary. But besides the radiative modes that cross the null boundary, there is additional data, and we will see how this will play out in a moment. We have corner data at the codimension 2 endpoints of this null boundary. And these are really charges dual to edge modes. And these edge modes play also an important role. We have briefly heard about this yesterday in Victoria's talk on quantum reference frames. So there's also a connection there. And this is really has been a field of very active and exciting developments during the past couple of years. Now, how to succeed, how to make this program work. So what we need to do are, what I need to tell you now are 3 steps. First step is how to parameterize this data in terms of the geometry of the null cone. So I have to tell you about the state space. Next step is to equip the state space with the natural symplectic structure. Final state is to push towards quantum theory, and I will do that by using a truncation to a certain class of piecewise constant initial data. So step 1 is basic null surface geometry. So why is a null surface advantageous for us? It is advantageous because there is more structure available that we can use. If you take the pullback of the space-time metric to the null boundary, we get a metric, but this metric is degenerate. The unique degenerate direction is the direction of the light rays that rule this null hypersurface. So there is a bundle structure. We can think of the null boundary as a sort of fiber bundle with a base manifold, which is the 2-dimensional corner, a cut. And now, just like we have tetrads in 4 dimensions, triads on the 3-dimensional hypersurface, we have now dyads, so because there are only 2 of them, on the null hypersurface, on the null boundary. And now we want to parameterize them, use a useful way to parameterize our initial data. And what I use is the following. So there's a overall scale, an overall conformal factor that can vary along the entire null hypersurface. But besides the conformal factor, we have to parameterize the shape degrees of freedom, whether we are dealing that encode angles and shear degrees of freedom, and we can encode that into an SL2R group element. Okay, a sort of holonomy, as we will see later. And then what we keep fixed is kind of universal structure, namely the direction of these null rays. So I don't vary those. And on top of that, a fiducial background dyad. Take, for instance, this can be anything. Take, for instance, the dyad induced by the round metric on the 2-sphere boundary. If this if the base manifold is a 2-sphere, we can use this is a natural choice. And now the metric data, so this co-dyad, encodes the metric geometry on any possible cut of this null hypersurface. But and this is essentially a 2-dimensional metric geometry. But then we also have the direction of the null rays themselves. And now we need to speak about evolution along these null generators. So I need to introduce a notion of time. And for reasons that will be more clear on the next slide, the following choice turns out to be useful for us. So all different choices are basically related just by rescaling of the null vector. And a particular useful choice is where the non-affinity, so these are not affinely parameterized null geodesics, these have a non-vanishing affinity, is actually proportional to the expansion. And u is our time coordinate along this null direction. And furthermore, I'm considering here null hypersurfaces with a boundary, codimension 2 boundary, and I keep the boundary values fixed. And I call this clock teleological because it knows that it should assume certain values, in boundary values in the future before things have actually happened. So that's, I think, a nice name to call it. And as I said before, the non-affinity, so there is a non-vanishing affinity, and it's proportional to the expansion. And what I'm very excited about is that from a different approach, it has actually been turned out that this choice is indeed useful also for other reasons. So there's some agreement from different perspectives. Laurent and Ciambelli in their recent paper found exactly the same, and it took us some while to figure out that we are speaking about the same things, but this I found very encouraging, that there we are on the same track. Furthermore, by this definition, this time variable becomes field dependent itself. So it becomes part of phase space. Now, besides the parameterization of the geometry, we need to speak about the constraints. What turns this initial data to initial data for general relativity? And to satisfy this, we have to impose two constraints. Remember, if we, on a spatial hypersurface, we have the scalar constraint and the vector constraint. But if we push to the null boundary, we are only left with diffeomorphisms that move along the null generators. So we are dealing with less constraints. The problem becomes more and more tractable. And in fact, now I can tell you why this choice of time is useful and simplifies the problem, because this equation simplifies. Furthermore, if we push this geometry all the way to null infinity, this choice of time agrees with the asymptotic bonded time. Basically because so this has a non-affinity, but the non-affinity is proportional to the expansion, and the expansion vanishes asymptotically as 1 upon r. And, but on top of the Ricciardo equation, so the Ricciardo equation is just one component of the Einstein's equations, and it tells us in that gauge that the second time derivative of the conformal factor is proportional to the shear. And where do we get the shear from? It is encoded into the transport equation for this SL2R holonomy that encodes the shape degrees of freedom of the codiad. So this is what the conformal factor, this is area. But on top of area, we also have a codiad data, which is encoded into this SL2R holonomy. So here is the shear that determines this is basically a connection along the null rays, okay? It's a transport equation, and there is a U1 part, phi is a U1 angle or connection along this null rays. And J, X bar, and X, these are just the generators, these are matrices, generators of SL2R. So, this is an SL2R group element, this is an SL2R Lie algebra element, and its components with respect to a canonical basis are a U1 connection and the shear that then enters into the Ricciardo equation. And they satisfy, J is basically a complex structure. So this is the data, okay? Data and constraints. Next step is to go to the symplectic structure. Now we want to connect now loop quantum gravity with the geometry, quantum geometry of the null cone. So the action that we choose is our gamma Palatini action. Again, this is something that we only have in 4 dimensions. So just like there is this weird coincidence with the Planck power, there is also this action only appearing in 4 space-time dimensions. And why do we need to speak about the symplectic structure, symplectic potential? Well, because it encodes the algebra of observables at the classical level in the h bar going to 0 limit. And then if we do that, if we start from this action and evaluate the symplectic current and compute the symplectic potential on the null hypersurface, we find the following expression. The first line is the only instant where gamma actually appears. And it gives the corner phase space. The next line gives the free radiative data. And then there's the and I will speak about this in a moment. And then there's the final line where we get the constraint. So what is written here is the Raychaudhuri constraint, and it is conjugate on phase space to our choice of time. Okay, this this bold phase D's, they are differentials on phase space. I use a different notation to distinguish it from differentials on space-time, which is standard in our community. And notice here, this is also something that Aldo, Enrique Gomez, also Laurent, and Ciambelli and collaborators introduced. This is a dressed differential, or a sort of connection on field space. So a covariant derivative on field space, on phase space, and the covariant derivatives are distinguished from ordinary derivatives by connection, and the connection is basically is nothing else but a time reparameterization of time along the null generators. And this index I simply means that we are working in the interaction picture where this U1 phase has been absorbed back into a redefinition of the field variables. Now, notice something important. To solve the Raychaudhuri equation, we need initial data. So I have to give you the shear, but I also have to specify initial data for omega, for the conformal factor. I have to give, this is a second order ordinary differential equation, so I have to give two initial data. And one possible choice is to give initial data for omega on the initial and final cut. And this is precisely, and this now also has a phase space, this initial data. And it is this data, the corner phase space data, which is affected by the presence of the immersive parameter. Notice also that here, J is the complex structure, it is the U1 generator. So we have something like a U1 angle being conjugate to the area. This is the origin of the area quantization on the null cone. And now we can ask, so now we understand the structure of this equation. So we have constraints, free radiative data, and corner data that gives the initial data for solving the Raychaudhuri equation on the null cone. And now we can ask to quantize this. Now this is difficult. It is difficult because these fields, when solving this constraint, these fields will depend in a highly nonlinear way on all the free data. So this is just, there's a conservation of difficulty. So we need to do something that makes our life simpler. And what I propose is a truncation. The basic idea is that, well, the shear is the free radiative data on the null hypersurface. For quantizing generic initial data is perhaps hard, perhaps too hard. But what we can do is to restrict ourselves to a specific class, namely a class of initial data where the shear is piecewise constant. And then the logic would be that any arbitrary initial data can be approximated to arbitrarily good precision by a sequence of such pulses. Whether this is true also at the quantum level, I do not know, but I hope it is. And then we are and then the idea is to quantize each of these pulses individually. But since we are now in a finite, now each pulse is just characterized by finitely many degrees of freedom, so we have reduced everything to a finite dimensional mechanical problem. Furthermore, the algebra, the phase space is local along the null rays, but ultra-local, the Poisson brackets are ultra-local in the angular direction. So a sort of topological quantization, or what Laurent calls a molecular approach, is actually not that unnatural. It is actually perhaps what one should do. Furthermore, the length of this, the duration of this pulse is just a coordinate. I set initial values to some arbitrary choice. So there is no, I said u equal -1 at the initial cut, +1 at the final cut. So there is no scale at that point. This is a cutoff or a truncation, but at that stage, there's nothing that tells us that is a very short pulse in physical units or a very long pulse. So this is neither a UIR nor a UV cutoff. And each pulse I call a quasi-local graviton. Okay? And the idea is now to quantize such quasi-local gravitons. And the condition is that the shear is constant in this time direction. The U1 dressed shear. And this is a gauge invariant statement, because I told you what this time variable is physically. And now something happens, namely something strange in a way. Now you know why this is easy to solve. Now this is easy to solve, no? If sigma, sigma bar are constant, then this is just a constant. This is just like a harmonic oscillator, oscillating, no? Everyone can solve this. And similarly here, we don't need to use a path ordering to exponentiate this equation. We can just take the exponential. But now something strange happens, namely that with respect to the Ricciardo equation, the shear is an Euclidean angle. With respect to the holonomy equation, it is more like a boost angle. And what we will see in a moment is that the immersive parameter, Barbero immersive parameter, kind of mixes the two, which is reminiscent of what happens on a spatial hypersurface, where extrinsic and intrinsic angles or curvature are mixed by the immersive parameter. So something similar happens on the null cone. What is the phase space that we get at the kinematical level? I get two, for each pulse, I get two Heisenberg charges, then an SL2R algebra, and a set of angle-dependent group elements where these operators can act upon. So this looks like a simple phase space, but what is highly nonlinear is the relationship to the original geometric data. For instance, the area densities, so these are our half densities. So the area density of at the two cuts will be a mixture of equation and of number operators and the magnetic quantum number that appears in here. And here you see that now the shear in this equation appears with the immersive parameter. And this is this kind of mixing that I mentioned earlier, that the immersive parameter allows you to add boost angles into a U1 phase, turn boost angles into a U1 phase. Now, what about physical states? The phase space I introduced on the previous slide is a kinematical phase space, but there is now only one constraint left, and it assumes the form of a recurrence relation that involves the Heisenberg charges, creation operators, and the SL2R step operator. And on the right-hand side of this recurrence, of this constraint, you only have operators that only number operators. So the U1 generator in your SL2R and the number operators for the Heisenberg charges. So this is an SL2R ladder operator. And this equation can be solved. Furthermore, the constraint, so this is a constraint, trivially commutes with the SL2R Casimir, which means that you can classify physical states by the value of the Casimir. And what is the value of the Casimir? Well, it's L squared minus CC bar, okay? But if you express this in terms of the original geometric data, you get something very wild. So I was first shocked at looking at this equation. And again, you see something I mentioned before, that the shear now appears in both as a Lorentzian boost angle as well in this equation, as well as a Euclidean angle. And what mixes the two, so here is a hyperbolic sine, here is a tangent, and what mixes these two terms is the immersive parameter. And now we can solve this recurrence relation using SL2R irreducible unitary representations. In SL2R, there are two series. There are continuous series representations and discrete series representations. And they are distinguished by the value the Casimir takes. So if the magnetic quantum number wins, then we are in the discrete series representations. And it turns out in that case that something interesting is happening. You can solve these recurrence relations with a finite number of steps. The recurrence relations terminate at some point. They terminate basically because the U1 generator is bounded from below in the discrete series representations. And that translates in the boundedness of the shear. On the other hand, if we are in the other series, when the shear degrees of freedom in SL2R win, then we are in the continuous series representations. And the Casimir takes, the spectrum of the Casimir will be continuous. And now the magnetic quantum number is no longer unbounded, bounded from below, it is unbounded, and these recurrence relations never stop. So physical states are an infinite sum of these kinematical states. And now you can ask, well, what is the value of the shear where you go from one representation into a different representation? Okay, now this, let me just jump back. This seems difficult to solve. You have, let's fix omega plus, omega minus, and you want to solve this equation for the shear given the left-hand side is 0. Well, looks a bit difficult. But let's solve this for small shear. For small shear, the tangent is just, they have the same behavior. No? Hyperbolic sine and tangent, they start out linearly. So for small shear, we can evaluate the, we can find the critical value analytically. And it's this expression. And now you can ask, well, everything I told you about is at the finite null boundary. What happens to this expression when we take it all the way to null infinity? Now this is a classical equation. When answering this question, I'm making an assumption, namely that the semi-classical limit exists, and it makes sense to take this quantum description to null infinity, assuming the existence of semi-classical states where these become just C numbers. And then the only difficulty is to embed this pulse into boundary coordinates at null infinity and taking advantage of the fall-off that we know. So we know, for instance, that omega, the conformal factor, will go as R squared. This difference will go only as R linearly, because the leading order cancels and so on. So we just insert the fall-off conditions, the leading and sub-leading orders of the conformal factor. And if you do that, and also translate the time coordinate, this teleological time that starts at -1 and goes to 1 during the duration of the pulse. And if we translate this into Bondi coordinates, this will have a certain, this pulse will start at a certain value of time and finish at a certain value of Bondi time. Then we can translate this value for the shear into Bondi frames, into the standard Bondi coordinates. And then we can use the Bondi mass loss formula to ask at what luminosity does the transition happen. And this is what I get. So I get that the critical luminosity at which we go from discrete series representations to continuous series representations happens at an order of the Planck power. And the immersive parameter appears in this funny way. So in particular, if we were to send gamma to infinity, this would be 0. So a very large value of the immersive parameter can be excluded. On the other hand, it doesn't disappear if we send gamma to 0. So that's a bit odd. But that's what I get. So let me summarize. And before concluding and summarizing, let me briefly mention that physics goes on, and we will continue to develop ideas and research on quantum black holes and the relation to asymptotic infinity. So if you want to join our workshop in Erlangen, reach out to our organizers here at FRU, Mushin Han and Jonathan Engel, or there at FAU in Erlangen to Christina Giesel. So let me summarize. What I told you about is a non-perturbative quantization of impulsive null initial data. The quantum geometry that we get includes a quantization of radiative data of the pulse, but also the quantization of additional area data, corner data. And the quantization of the corner data is actually what we had all the time in loop quantum gravity, quantization of area. But there's something on top of that. Not only the radiative data, but also additional corner data for frame fields at the cut. This is also something you heard in Mark's talk on Tuesday, I think. And then what I find is that in this truncation to piecewise constant initial data, I find a bound, namely that the Planck power separates the discrete and continuous SL2R representations. And I have indications that above the Planck power, states contain caustics, basically because there's this infinite, recurrence relation never stops. And this seems to be in conflict with the implicit assumption in making this connection to null infinity, that there exists a smooth, exist nice semi-classical states at future null infinity. So the question that I want to pose is whether we can assume that classical GR applies when one Planck energy quantum is radiated away during one Planck unit of time. And I think it does not. If there is a fundamental UV finite theory, this should not be possible. But since H bar cancels out of the fraction of the power, this may survive in the semi-classical limit. So these are the conjectures that the Planck power places an upper bound on semi-classical states, because there's a built-in UV cutoff in non-perturbative quantum gravity. And loop quantum gravity has a mechanism for achieving that by quantizing geometry. And a bit more wild, perhaps, that the Planck power plays for quantum gravity in d = 4 the same role as the Planck mass in d = 3, and that there is an opportunity to develop an interesting new phenomenology, just like what relative locality and Kappa Poincare did for 3D gravity, what Florian is very knowledgeable about, and Laurent and so on, that this that something similar could be developed in 4D. Thank you for the attention.
Thank you. Questions, comments? In that corner, there are a lot. So, if but okay.
You first.
Sorry. The question is, there's something I didn't understand. Maybe you said it. If at null infinity, there's an ADM Hamiltonian, and one nice property of the ADM Hamiltonian is it's positive, and so we have a vacuum, or maybe at least some set of vacua labeled by super translations. I didn't understand what the analog of that here would be, because if you're in a finite region, there's a Casimir effect. Now there's a modular Hamiltonian that's positive, but that's not related in any nice way by the constraints, as far as I know. So what is the analog of the vacuum and the positivity of the ADM Hamiltonian for this null surface?
Thank you for this interesting question. So this is really, I think, a challenge. So I don't because I don't know the answer to this question. But this is something we should find, and perhaps perhaps there is no unique vacuum, Perhaps there is perhaps there are many states that can be used as perhaps there's a vacuum degeneracy in the finite region. But I would expect that but in principle we have this modular Hamiltonian. We have a generator for internal boosts, and this is just the area. Thank you.
So thank you so much, Wolfgang, for all the work that took to this beautiful result, and indeed it's very exciting to think about the phenomenology that comes with it. And something to which we have to hold is the fact that so there is already an observations of a bound in the luminosity. So this is something that people are already observing with LIGO and so on. So I wanted to understand better. Are you saying that the bigger the black holes, the more we will be able to observe this effect?
So thanks for this question. I'm not very knowledgeable about phenomenology, but I remember our discussion at the conference in Austria, and you said something very interesting, namely that so it is true that the peak luminosity doesn't change when is not extensive. If we make the black holes twice as big, we should not expect that this changes. But what can change if we look further back in the universe to older and older events, and then we could see that there is that we don't see anymore coalescing black holes very early in the universe with a certain luminosity. Yeah.
Wolfgang, I was interested, am I correct in thinking that for your gamma, I would be the self-dual limit of the theory? Is that right?
Correct.
So I was interested to see that for gamma equals I, you have a divergence in the peak luminosity. in your formula. And so I was just curious if you had thoughts about what that divergence means here.
So this would not be a contradiction. This is what we would have in classical GR. Classical GR, there is, from the perspective of the physics at null infinity, there's no reason to believe in a luminosity bound. If you only look at in the radiative phase space that Abai introduced. So I agree that from that perspective, there is a priori no reason to believe that such a bound should be there. But then, so this would be just would just be compatible with the classical picture. But I don't believe, I don't think, so what makes loop quantum gravity interesting? Why is it, why does it fascinate us? It fascinates us because it has a mechanism for quantum geometry, derived not ad hoc as in other approaches, but coming from a classical action and so that's why I'm interested in keeping gamma real.
Okay, thanks, Wolfgang, for this beautiful talk, very inspiring. It's packed with results. I have maybe kind of, if I'm allowed, kind of two questions. One is more technical. I want to understand, go back to this Casimir, and you wrote the formula for the Casimir. But I'd like to understand, can I get an understanding of, you know, the meaning of this Casimir in some kind of semi-classical limit? Like, I mean, here it's kind of a function of the power spectra, like the sigma square, but you had this, you know, analysis, which is very algebraic. Is there some kind of semi-classical, coherent or geometrical understanding of what is this, you know, the geometry of that Casimir, what it represents? Because it plays a key role in your...
It plays a key role.
Yeah.
It plays a key... In
so,
fact,
so usually, I mean, you see, usually we have this kind of corner chart. I mean, yeah, is there some kind of...
so it is not a corner charge, because it knows about the radiative data.
Yeah.
And furthermore, you see it also here, if we drop gamma, only this term survives. So this is the Palatini term, if you wish, that only contains G Newton, not the immersive parameter. And this is manifestly negative.
So can I think of it as a, I don't know, an on-shell action or something like that in the continuum? Okay, maybe,
yeah,
maybe we
I
can
thought about in that way.
Yeah. And maybe
but
if
it classifies the representations that can appear.
So if I may, maybe for the second part of the talk, so what you prove is there's kind of a transition. So this criticality, it only becomes a bound if you say I'm not allowed to have continuous series representation, right?
That's right. So I want to be, I want to leave this question a bit open. Mm-hmm. So at that stage, I do not say that the continuous spectrum is not allowed. What I say is that a transition happens between, like in the hydrogen atom, where there are bound states and continuous states. What I want to understand better is whether the states with the continuous spectrum have also a good semi-classical interpretation, and I have some indications that they have not, but this needs to be better understood at that stage.
Okay, and maybe on that point, if I'm allowed. So I think what you showed in the end is something very interesting. So usually when people talk about asymptotic infinity, it's an order of limit. They first take, you know,
yes.
R to infinity, and then there, you know, we can construct the phase space and it's unbounded. But somehow you kind of, and then there's this proof, so-called proof that infinity, you know, sky is a nice null surface that goes from my. But what's interesting in your statement, it was only en passant, you're kind of challenging that picture. You're saying, no, in fact, the proper way to take infinity, there should be an infrared cutoff first.
Absolutely.
And if you have an infrared cutoff, there will be caustics that will prevent you from proving yes. this so-called structure of infinity. So, okay, I mean,
yes,
in some sense, you're kind of challenging the status quo, the mathematical status quo of what is infinity. That's a big
yes.
statement.
So what I want to challenge is the idea that these two limits commute, that you can go to null infinity and then quantize, or first quantize and then go to null infinity. Because what we are sending here to infinity are basically quantum operators. And by assuming that an operator assumes that has only very specific eigenvalues, maybe in contradiction with the Heisenberg uncertainty principle. So we cannot just go to a very sharp state that sends us to infinity. Perhaps this is not possible because these two limits may not commute.
Wolfgang, I find this result beautiful. The fact that you find an observable, a physical observable, you can quantize it, you find this transition in the spectrum that gives you a maximum power. Maximum power depends on gamma, so observationally gamma, if one takes it seriously, gamma cannot be larger than 10, because otherwise it would already be in tension with black hole mergers observed. The question that I have is, so this is total power in gravitational radiation. Have you tried to look at, so there's a gamma. We know that gamma appears together with parity violation. We have seen it in more than one way. We look quantum gravity and spin forms. Is there a way to look at the power only in each one of the polarizations? Does it depend on gamma, and how does it depend on gamma?
Yeah, I have not looked at this yet. One reason is that perhaps I'm a bit puzzled by how to do that, because at the on a null boundary the phase space is smaller, so you have two you lose the modes that go along the null direction, and I think to answer your question, I would have to do something like in-out and this is now kind of the next step, or to understand the S matrix in this formalism. What the spin form amplitudes are supposed to give us, and namely transition amplitudes.
Thank you.
Thank you for the beautiful talk, Wolfgang. I wanted to know what happens if you take out the emergency parameter from the very beginning. So of course, naively, you said it would sort of make the limit of the luminosity bound sort of go to 0, which would say something like you only have the continuous representations, if I understood right. But that also sounds like it's a degenerate limit. So what happens if you do it from the very beginning?
Then I would, thanks for this important question. Then we would end up in an altogether different representation of the canonical commutation relations. So it's not that I'm saying if I send gamma to infinity, there can be no gravitational waves in the quantum theory. That would be silly. What I'm saying is that if we start out with a theory where gamma has not a large value, let's say, but is sent to infinity before quantizing, what then happens is that the area is, so this corner data for the area is conjugate to a boost angle. There's no discreteness in the area spectrum, and I end up in an altogether different Hilbert space, where perhaps the theory is no longer UV finite.
Okay, thank you.
I have also some questions. So in your approach, you assume that this expansion is not 0. So does it have a good limit to the non-expanding surface?
I think you were, so you're mistaken.
Oh, sorry.
So in fact, so there is no such assumption.
Oh, I see. So
If the expansion can vanish, and well, no, don't. The expansion can vanish, and then so what you're basically asking is what happens if I try to understand an isolated horizon. What happens then is that the shear vanishes. This U time coordinate, this teleological clock, is an affine parameter, and we go back to the quantization of an isolated horizon that you and Ashteka and Krasnov and collaborators developed.
Okay, good. So thank you for clarification. And another question, also the technical. So you use Palatini formulation, so the classical variables are triads, are frames rather than metric. So there are those gauge transformations, so Lorentz transformations of frame. So in what way do you handle this?
So, but you have to understand, I'm working on a null hypersurface. So the local gauge group of frame rotations is no longer SU2 as on a space-like hypersurface. I've basically reduced everything to a U1, namely rotations in the plane of the cut, let's say. And these are conjugate to a gauge generator, which at the corner has an edge mode and becomes physical. And the charge for this U1 is the area, which then explains why there can be discreteness of area at the quantum level.
Okay, thank you. If there are no more questions, let us thank Wolfgang again.